This webinar corresponds to the lecture on vascular flow and resistance. What we are about to do is we're moving away from the heart and now moving into the circulation. Now, this lecture is designed to go over the major components of your circulation, looking at their functions, looking at various volumes that we have, compare them amongst the different components of the circulation under resting conditions. We're going to look at some major concepts: the relationship between cross-sectional area and velocity of blood flow, and factors that affect blood flow, various factors such as resistance or viscosity. We are also going to be looking at different types of flow, such as laminar and turbulent blood flow, and why it's clinically significant. After this lecture, we will be continuing on with the circulation, looking more in different parts of the circulation and other major concepts associated with circulation, such as blood pressure and its regulation, and blood flow and its regulation, how we regulate cardiac output, and things like venous return. But today we're just going to be looking at vascular flow and resistance. Before we start, let's do a little bit of an overview. What's the functions of your circulatory system? Well, the circulatory system, you think about, well, it should be about transport. So they'll be transporting things like hormones, waste products away from tissues where they were generated. They transport nutrients to tissues. They're about maintaining an appropriate environment for that tissue at that appropriate time. We have two major components of our circulation. We have the systemic, which is a larger circulation. They also refer to it as your peripheral circulation, since it supplies all the tissues of the body except the lungs. And we're also going to be looking at the pulmonary circulation. This one services the lungs, and it's a smaller circulation. There's a big difference between these two circulations in not only their size, but in the pressures that you encounter in these circulations and the resistance. The systemic circulation is considered to be a high pressure, high resistance circulation. If you look at the aortic pressure, it goes from 120 during systole down to 80 during diastole. Of course, that's Guyton numbers. When you look at the pulmonary circulation, the pressures are much lower. The resistance in that circulation is much lower. The pressures in the pulmonary trunk go from 25 or 30 millimeters of mercury during systole and go down to about 8 millimeters of mercury during diastole. So it's a much lower pressure circulation. We are going to be predominantly, for the next few weeks, be discussing the systemic circulation. Every once in a while we'll bring the pulmonary circulation back in, but we will be concentrating more on the pulmonary section, our pulmonary circulation, towards the end, right before we start looking into the respiratory system. What we're going to be doing first is we're going to be looking at the different components of the circulation, looking at the elastic arteries, like the aorta, the muscular arteries, arterioles, and there's more than one type of arterial. We're going to be looking at the capillaries, where exchange will take place. We'll look at the veins or the venules and what their functions are. So what I'm going to do first is go through the different components of the circulation. This is something you have discussed in cells and tissues, so I'm not going to discuss every little thing like you see in the pictures in your notes. I'm just going to give you some general overall things concerning these vessels and their main functions. So I'm going to start over here on the side where we're going to start with the elastic arteries, and specifically if you start with the aorta is an elastic artery, and its big thing was to allow you to maintain blood pressure due to its being elastic. The arteries in general, especially when you start looking at the muscular arteries, they're very thick-walled tubes. And why are they so thick-walled? Well, they have strong walls because they have to transport blood under a very high pressure to the tissues. There is a lot of resistance along the arteries, and also when you start getting to the arterioles, there's a resistance to flow, But one of the functions of that is to reduce pressure. So by the time you get to the capillaries, that you won't have really high pressures, because what would happen, the capillaries are so thin-walled, you damage the capillaries. Now we're going to be looking at where really most of the pressure drops, and we'll have a picture later on that will show you, will take place in the arterioles. Now your notes may be off a little bit, but I want to make a distinction of the function of the arteries and the arterioles. The arteries is about transporting blood under high pressure and eventually to the arterioles. Now the arterioles are the ones that are going to be really responsible for reducing pulse pressure and blood flow. They're going to be the ones that are responsible for eventually controlling how much blood will actually go into the capillary beds. So it's not really the arteries, it's the arterioles. Now you have two types of arterioles, and you have in your notes resistance and true arterioles. There's a difference in their size. The resistance arterioles, these are between 100 and 300 micrometers in diameter. They are obviously larger. They have a very high resistance to reduce pressure before blood enters the capillaries. So they are going to be reducing the pulse pressure in blood flow. The true arterioles are less than 100 micrometers in diameter. Their job is to control how much blood gets into the capillary beds. So through these guys have things called precapillary sphincters. And the precapillary sphincters act as control valves through which blood enters the capillaries. And we'll be looking at how they're controlled at a later date. Once you get down to the capillaries are thin-walled vessels. Their whole job is to exchange nutrients between blood and the interstitial fluid. They're very thin walls. They have pores. There's absolutely no smooth muscle. It's just an endothelium and a basement membrane, or basal lamina. That's it. So it allows you to have the transport of gases, nutrients, waste products. It's all about transport, or exchange, I should say. Once you move on, you go into the venules, like the little veins. The venules and eventually will empty into the little medium-sized veins, then your larger veins like your vena cava. The veins, when you compare the veins versus the arteries, you'll notice the veins are much thinner walled, but they don't need to be thick walled because they're working under low pressure. But you'll also notice the lumens are much bigger than the corresponding sized arteries. The veins, big job of veins, is they act as a major reservoir of blood. So we're going to be looking at some blood volumes, and I'm going to prove it to you, that most of your blood volume at rest are in the veins. It's about storage of blood. Maybe I'll borrow it if I need to, say during exercise, and move it into the systemic circulation. So what we're going to do first is look at some volumes. And you have a little pie chart here. We're looking at blood volumes at rest. And I hate to say it, but you do have to know some numbers. Not every number that you see on your page, but a large amount of them. So just pay attention. You'll know which numbers you need to know. You'll notice these are blood volumes at rest. So you're just hanging out, barely, listening, or barely awake. Some of you may be drooling at this moment, but I hope not. We're not that far into the lecture. So if you'll notice, in the overall total circulation, 84% is in the systemic circulation. That leaves 16% in the hearts and the lungs. So you have 16% here. The remaining 84% is in the systemic circulation. It's not so much you need to know those numbers, but if you do math, you'll be able to come back to get those numbers. What you need to know is you need to know, one, the percentage of the circulation that's in the venous circulation. And I should say specifically, first you should know the systemic venous circulation. And this is the number to know, is the 64%. You don't have to know these individual ones here, but you should know 64% of your blood volume at rest is in the systemic venous system. That's showing you, again, the job of the veins is about to be a major reservoir for blood. What leaves us, if you notice, we've got 13% in the systemic arterial system. You have 9% in the pulmonary, or in the lungs. You'll notice that in the heart and the capillaries, they both are 7%. They will always be equal to each other. The heart 7%, the capillaries are 7%, because what leaves the heart will eventually come and be what's in the capillaries. So they're always going to be the same. These numbers are dynamic. They're not static. So during, say for example, during exercise, you will see that you will start, the amount of blood in the systemic venous system will decrease, because some of that blood is being moved over to the arterial system over here, so, or in the systemic system, so you can increase your venous return and increase your cardiac output. So that's a kind of important concept to know, is that these numbers are not static. And when you say your venous return goes up, your cardiac output goes up, your blood volume going into the lungs are going to go up, because it's got to oxygenate that blood and get rid of CO2. But the pulmonary system is very well equipped to accommodate a much larger amount of blood, because they're specialized, and we'll be talking about that when we do the pulmonary system at a later date. What we're going to do next, here's a major concept associated with the circulation. It's the relationship between total cross-sectional area and the velocity of blood flow. But what I need to do first is define some of these terms, so you have a good understanding of what each of these terms mean. The V is the velocity. This is like speed. Think of it as speed. This tells you how fast blood flows past a certain point. So you'll notice down here we got like, or how much distance we have traveled per time. I've moved 10 centimeters in a second. The Q is our abbreviation for flow. Flow really means flow rate. This tells you the volume of blood that passes one point in the system per unit time. In our circulation, flow is expressed generally as liters per minute or mils per minute. I want you to think of your total blood flow. If I refer to something with what your total blood flow is, your total blood flow is equal to your cardiac output, which under resting conditions, what is the resting cardiac output? I'll let you try to remember that. Okay, it's something in liters per minute, and you're averaging the guys and girls together. The flow rate tells you how much blood's going past the point per time, and velocity is telling you how fast, or the distance it's moved per unit time. So a good analogy, you're looking through an open door in a hallway. The number of people passing the door in 1 minute is the flow rate. How quickly those people are walking past the door is their velocity. Now, the A refers to total cross-sectional area. And if you look at these little tubes, or these little cylinders, here we have one cylinder. We're going to say this represents your aorta, because you only have one aorta. These represent all your capillaries, and you've got a lot and lot of capillaries. So your total cross-sectional area of your capillaries is much bigger than in your aorta. So what we're going to be looking at is a relationship between velocity, flow rate, and total cross-sectional area. So just look at the equation, think of it as a concept and not math. According to the equation, if I increase flow, that's on the numerator, so if I increase that, what should happen to velocity? Well, that should go up. So it's a direct relationship. The cross-sectional area. That is on the denominator. So if that number increases, velocity of blood flow will decrease. And we're referring to total cross-sectional area when referring to that A. It's an indirect relationship. So if you look at here, you've got this one, which is our smallest total cross-sectional area, and we progressively get to a larger total cross-sectional area. You notice I've kept flow the same. The reason why I've done that is that in your circulation, flow stays relatively constant. Maybe at a certain few seconds it may change, but then it remains constant. So pretty much we're going to keep that constant. What we're going to do is look at what happens if you increase total cross-sectional area. You'll notice as your total cross-sectional area increases, your velocity of blood flow goes down. So it's again the same thing I had mentioned earlier. So I'm going to show it to you a different way. The same thing a different way. Here we have a tube. Part of that tube was narrow, and then all of a sudden it kind of gets bigger. So if you notice right here, this cross-sectional area is much smaller than here. In order to get the same flow rate, the same volume of fluid past each point, we're going to say 12 cubic centimeters, which is actually a milliliter, 12 mils move past this point and this point per minute. They're the same. How can you do that when this thing is much smaller? So the way you do it is, if you look down here, is at point X, the velocity is much faster than in here. You'll see that in your circulation. So anytime your total cross-sectional area increases, your velocity of blood flow decreases. Okay? Now you can see in our circulation the relationship, or what parts of our circulation have the highest total cross-sectional area and its relationship to velocity of blood flow. So if you notice here on this top picture, your capillaries have the largest total cross-sectional area. We have lots and lots and lots of capillaries. And you'll notice, look down at the bottom picture, the velocity of blood flow is the slowest. Why? But I need you to emphasize the primary determinant of velocity of blood flow is the total cross-sectional area of all the components, or all that component of the circulation, not the diameter of an individual vessel. It's the total cross-sectional area of those capillaries. So why is it so important that the velocity of blood flow decreases when we're in the capillaries? What's going on in the capillaries? Capillaries is all about exchange. So if you want the exchange you need, we may need to slow it down a little bit. Allows time for exchange between the bloods and the tissue cells. It makes perfect sense. You'll notice that the venules and the veins, if you just kind of compare it here versus over here, there's a little bit more total cross-sectional area in our venules and veins, and that is kind of try to illustrate the concept that the veins are about storage, that venous system is about storage again. So I just want to kind of just give you a reference, though, when you look at total cross-sectional area of capillaries versus the aorta. The total cross-sectional area of the aorta is 33 centimeters per second. And the capillaries is 0.3. Oh, sorry, I'm actually telling you the velocity. The aorta velocity is about 33 centimeters per second. In capillaries, it's 0.3 millimeters per second. That is a lot slower. I also want you to kind of envision something else when you think about cross-sectional area and velocity of blood flow. If you've ever watched a leaf float down a river, where the stream is narrow, the leaf moves very rapidly. Where it's wide, the velocity of the water drops and the leaf kind of goes down a little bit slower. It's very, if you think of it that way, it's a very easy concept to understand. And just think about what's so significant behind that. You want time for exchange, so it's going to be slower. Now this picture is in your notes, but it's obviously drawn a little bit different. But It's going to be on right after the notes. It's just that's on the next page in your picture, so you can kind of look at a picture corresponding to my picture. What we're going to be, I need to talk about briefly, is blood pressures in the various parts of your circulation. If you notice here, we're going to start up here in the aorta. Here's your systolic blood pressure, 120. Your diastolic blood pressure is 80. The difference between the two is your pulse pressure. So that'll be 40 millimeters of mercury. As you move down through the arterial system and get down to the arterioles, you notice this pulsatile flow starts to kind of get diminished. And by the time you make your way through the arterioles, that pulsatile flow is gone. Why is that so significant? Where is it predominantly taking place? The resistance arterioles. The resistance arterioles provide a lot of resistance. They're going to reduce pulse pressure, because by the time I make it my way to the capillaries, I do not want pulsatile flow through the capillaries. I want continuous flow through the capillaries. Also, I want you to notice this black line right here. This is representing what we call the mean arterial pressure, your average pressure in the circulation at that point in time. In the aorta, Guyton says the mean arterial pressure is 100 millimeters of mercury, just because he says that's an easier number to remember. It really is not 100 millimeters of mercury. It's more between like 93, 96 millimeters of mercury. And at a later date, we'll show you how we calculate mean arterial pressure. But right now, I want you to notice that the mean arterial pressure is the highest up in the aorta, and it steadily declines as we move through the arterial system. Once you get through those resistance arterioles again, you're going to reduce that pressure significantly. So by the time you make your way to the capillaries, the pressure is much lower, so we don't damage the capillaries, blow them out, because those walls are so thin-walled. The capillaries, here's a number, yet another number to know. The average capillary pressure in the systemic circulation is about 17.3 millimeters of mercury. This will not be the only time you ever hear that number, but it's about 17.3 millimeters of mercury. So there's been a significant drop. It's plenty. We'll still be able to have enough pressure so I can get exchange there in the capillaries. That pressure will continue to drop. By the time you make it to the right atrium, that pressure at the right atrium should be near zero. So right before it enters the right atrium, it's going to be about 0 millimeters of mercury. Before we start looking at relationships between flow and resistance and pressure, I want to just mention 3 things about the circulation and explain to you that at later dates, later lectures, we will be talking a little bit more in depth about each of these concepts. Obviously, we're starting to talk about flow a little bit today because we're going to be looking at things that can determine or affect flow. But flow, we will be doing a whole lecture on what controls blood flow. And blood flow in each tissue bed is very precisely controlled by your metabolism. So if, say, you're exercising, active tissues are going to require more blood flow. So certain factors that are being produced or things that are needed by that tissue are going to cause an increase in blood flow to that tissues. We will not increase flow to every part of our body. We will increase flow to the parts of the body that need it, not to every part. So we'll have to talk about how we control blood flow using the nervous system and also looking at local control of blood flow. But those are topics for a later time. Cardiac output, you already know the equation, or one of the equations for cardiac output. It's heart rate times stroke volume. This is controlled mainly by the sum of all your local flows, because all your local flows in your tissues eventually come back to your heart and become your cardiac output. So we will also look at what controls that. We'll look at how the nervous system affects it, but also how local factors affect cardiac output. The last topic will be blood pressure. And blood pressure is controlled independently of either flow or cardiac output. It's controlled completely separately from the two. We will be looking at how the nervous system controls blood pressure and also how the kidneys play a role in your blood pressure regulation. Now what we're going to do next is look at some big concepts which are very logical. If you think logically, makes perfect sense. So what I want to do is you're going to look at this equation. Do you have to memorize it? Well, if you kind of have a general idea about it, then you can explain anything in regards to if I change any of these letters, and I'm not going to give it to you as in delta or lambda or any of that. If I say if something happens to the pressure, you should be able to tell me what happens to flow. So again, think of the equation not as math, but rather a conceptual equation. So if you notice this equation, the Q is flow, and what we're looking at for is the flow equation for an individual vessel. So this applies to an individual blood vessel. Again, I want to state that the flow in your entire system remains pretty constant. It's a steady state. An individual vessel can change moment to moment. So I'm looking at factors that can affect flow in an individual vessel moment to moment. So if you notice the first thing, delta P. Okay? Delta P refers to your pressure difference or your pressure gradient. The difference in pressure from, say, point A, which we have as P1, and point B, which is P2. What's the difference in pressure? If you look at the equation, the delta P is on the numerator. So there's a completely direct relationship between pressure difference and flow rate. So if I increase pressure, flow will increase. If you decrease pressure, you will decrease flow. That's if you don't change anything else. So that's what we're saying. So there's a direct relationship. Now I want to show you a picture. I want to emphasize that it's a pressure difference, not absolute pressure. So if you look at these pictures, the middle picture, there is no difference in pressure, so there's no flow. No pressure difference, no flow. Remember I said one of the things that rule physiology, gotta have pressure gradients. No pressure gradient, no flow. If you look at the top picture, the difference in pressure is 40 millimeters of mercury. Over here it's 100 millimeters of mercury. Over here is 60. So we have a flow rate of 20 mils per minute. The very bottom picture, you have the same flow rate because you have the same pressure difference. It's 40 millimeters of mercury. You notice this side's 200 millimeters of mercury. This one up here was 100. So it's not absolute pressure, it's the difference in pressure. That's what is going to determine flow rate. If you go back to this equation, I want you to give you a little breather here, cross out pi and cross out 8. Those are constants. Obviously, they're just part of this equation, so you can ignore those. Those aren't going to change. I want to look at the little r. That refers to your radius of the vessel. And you notice it's r to the 4th power. So radius, since it's on the numerator, that if there's an increase in radius, you'll have an increase in flow. If you decrease radius, you will decrease flow. It's a direct relationship. And you notice since it's r to the 4th power, just small changes in the radius will cause a very large change in flow. That might be an important thing for me to maybe use physiologically to control blood flow since it has such a dramatic effect on flow. If you look at the denominator of the equation, you have your lambda, which refers to the length of the tube. Over here, this is the Greek letter eta. This refers to the viscosity of the fluid. The length of the tube rarely changes, but say it may change during like growth, rapid growth or things like that, but it rarely changes. But we still have to go over what's the relationship between length of the tube and flow. The longer the tube, the lower the flow. The shorter the tube, the greater the flow. It's an indirect relationship. I want you to kind of think of if you have a really, really long tube and you're trying to fill up a bucket versus someone who's got a really short tube. Who's going to fill up their bucket quicker? The person with the shorter tube. It's got a lot longer distance to travel to get into that bucket. So you want the shorter tube. The viscosity of the fluid. This is also has an indirect relationship. So the viscosity, blood viscosity, viscosity in general is like internal resistance to flow that all fluids have. And you think of it somehow related to the stickiness or thickness of the fluid. The greater the viscosity, the less easily molecules slide past one another. And therefore it's going to be more difficult to get it and keep it moving. So under normal conditions, viscosity is relatively constant except for maybe some clinical conditions such as if you're dehydrated or if you have a condition called polycythemia where you make an abnormal amount of red blood cells, which are not normal red blood cells. So the blood becomes a little bit thicker. So if you increase viscosity, it decreases flow. So those are the different relationships. Here's another way of looking at flow. All I did was take that equation that you just saw, rearranged it, and I've made these things over here, the viscosity and the lambda, which is the eta, the lambda is the length of the tube, the radius. These things are all component of what we call R, or resistance. If I say you're resistant to something, you don't want, it's an impediment to something. You don't want it to move forward. So when we talk about their circulation, resistance refers to an impediment to flow. If you notice, just look at this down here. What components are increased resistance? What components decrease resistance? If you notice viscosity and length, those, if they increase resistance. So if you look at this equation here, again, if you increase resistance, you will have less flow. You're opposing it coming through. If you look here, the radius of the tube, if you increase radius, that decreases resistance. And so flow increases. The biggest component of your vessels that provides resistance is the friction that comes along the vessel walls. So if you increase the diameter, you have less friction along those walls. And if you just also think of it in regards to the length of the tube, if you've got a really long tube, you're encountering a lot of friction along the length of the tube. So if you notice the equation, if you increase resistance, flow goes down. If you decrease resistance, flow goes up. And obviously, again, what we'd mentioned before, pressure has a direct relationship with flow. Now, if you look at here, we have a large vessel and a small vessel. We have shown you the relationship between the size of the tube and the flow. And since it's r to the fourth, the radius has a very dramatic effect, which would ultimately, you can say radius it's just half of your diameter. Diameter or radius of a tube, if you change it, it has a very significant effects on blood flow. So one way of looking at it is, actually let's go back real second, we'll wait. I'll mention some terms with you in a little bit. Okay. So here, if you look at this tube, is showing you the pressure difference and the resistance the blood is encountering along the side of the tube. We need to look at something in regards to resistance to flow when we talk about the two circulations, the systemic and the pulmonary circulation. So they use a terminology called peripheral resistance units when they're trying to talk about resistance in the circulation. Resistance is hard to measure directly, but you can calculate it from measurements of blood flow and pressure differences, because here's the equation right here. So if they know the pressure difference and they know the flow rate, they can calculate resistance. So for example, if the pressure difference between 2 points is 1 millimeter of mercury and the flow is 1 mil per second, the resistance is 1, and they're going to say 1 peripheral resistance unit. In the systemic circulation, they say the peripheral resistance units is 1 peripheral resistant unit. If you notice, the pulmonary circulation is only 0.14. Now, I don't care that you know that number, 0.14, but I want you to know, or be able to tell me, that the pulmonary circulation has a much lower resistance than the systemic circulation. And I had mentioned that to you earlier at the very beginning of the lecture. But I can ask you a question, is if the pulmonary circulation has a much lower resistance, does it have a greater flow? Someone will say, well, yeah. No. The pulmonary and the systemic circulations have the same flow. The pulmonary system has a much lower resistance and a much lower pressure. So it ends up going where the flow is the same between the two. So I could ask it a different way, is how come the pulmonary circulation has the same flow rate as the systemic circulation if its pressure gradient is so low? It's because its resistance is so low. Now I want to, before I move on to this, what we have here, is I'm going to go back, so I just want you to envision something. And maybe we can do, at some point, maybe bring stuff in and illustrate it for you. If you ever drank through a straw, I would think most of you have drank liquids through a straw, you've always experienced the effects of resistance. So if you drank through a wide straw, you notice it was easier to drink through a wide straw than a narrow one, because remember, the diameter, the radius, affects resistance. It's also easier to drink through a short straw than through a long one. That's that concept of the length of the tube, the lambda. If you try to drink a milkshake, in some of these places you're like, you have to pull out the spoon because it's really almost impossible to drink it through a straw. But if you try to drink a milkshake through a straw and then try to drink a soda, which is easier to drink? The soda, because the viscosity is less. So the more viscous the solution, the liquid, the higher the resistance. It's going to be harder to get that flow. If I have to try to get the same flow rate up through that straw as someone drinking a soda, you're going to have to create a lot of little suction there, a lot of pressure to kind of suck it in your mouth. So think about resistance depends on things like the nature of the fluid, like its viscosity, and the dimensions of the tube, its length, and its diameter or radius. Now here's showing you again the idea of the radius and its effects on flow, and obviously its effects on resistance, which affect flow. And why I'm kind of spending a little bit more time on this is that this is how we physiologically regulate flow, is by changing vessel diameter. We can change pressure gradient, but that has a much more global effect. If I just need to increase flow, say, to my leg muscles while I'm running, I don't want to have to increase my blood pressure sky high just to get more blood flow to those leg muscles. I'm going to locally control the vessels in those leg muscles. I don't want to increase pressure all across the board. So physiologically, we regulate flow by affecting resistance, and we do it by changing the radius. So here we have a blood vessel, and your blood vessels are predominantly innervated by the sympathetic nervous system, that component of the autonomic nervous system. Parasympathetics, pretty much I want you to think of parasympathetics do not innervate blood vessels. It's sympathetics. The most blood vessels that have alpha-1 adrenergic receptors, they will bind to norepinephrine that's released by the sympathetic nerve endings. And what they do is if you have more norepinephrine being released, they will constrict. And what it does, it increases the fire. If you have an increased firing rate from the sympathetic neurons, releases more norepinephrine, a blood vessel constricts. If you have a decreased firing rate, the blood vessel will dilate. Your blood vessels have a tonic state of contraction. They have some tone to them. And so how you affect the diameter is by affecting the firing rate from the sympathetic nervous system. So if you increase firing rate, the vessel will constrict. If you decrease firing rate, blood vessels dilate. Now this applies to blood vessels that have the alpha-1 adrenergic receptors. It's a different story if you have a beta-2 adrenergic receptors, but they're going to be in what I will call protected circulations. And so they will be a separate story, but I want you to think of overall, general picture. Sympathetics constrict blood vessels in general. And they have to bind, though, through the alpha-1 adrenergic receptor. So it is the alpha-1 adrenergic receptors. Now here, let's see if you can see these concepts again. So I have a picture that shows you I have 4 blood vessels that are identical. What you'll notice is blood flow in is equal to blood flow out. So what would happen if I constrict this vessel? What's going to happen to blood flow through the whole system or through each vessel? So think about it. If I constrict this vessel, what's going to happen? Well, you'll notice is flow decreases because you've decreased diameter or radius of that vessel. You've increased resistance, so less flow. But where did that blood go? It's diverted to the other vessels. So the flow rate increases here. But what you'll notice, total flow is the same. This is what happens in our bodies. My total flow will always be the same, but in individual bed I may divert blood from one capillary bed to go into another capillary bed. So if I'm exercising, I may reduce blood flow to the GI tract and direct it over to my muscles in my legs or my arms or my abs, depending on what exercise you're doing. You divert it away from where you don't really need it to places that you need it. The total flow is the same though. What's coming in is what's coming back. So here's another concept check. I'm not going to answer these for you now, but I will answer these for you at a later date. So you've got 2 tubes. The pressures are shown at the ends. The tubes are identical. The diameters, length of the tubes are identical. So we have, the only difference is our delta P. So which tube will have the greater flow? So that's your first question. The second one, and this is lovely that it got all messed up, but just ignore it. I have 4 tubes here. We're saying that they have the same delta P, the same driving pressure. Which of these 4 tubes has the greatest flow and why? Which of those 4 tubes has the least flow and why? Okay. When we look at our circulation overall, we have to do a little physics review, just a real brief physics review. And I don't remember a lot of physics, but this is one thing I remembered when I learned physics years and years and years ago. I remember the difference between something in series and something in parallel. So we're going to apply this to our circulation. If you have something set up in series, the resistance of each component is additive. So we'll say this here is R1, this is R2, this is R3. So your total resistance is equal to all of these resistances added up. So if you have a circulation set up in series, you're going to have a higher resistance. If you have something set up in parallel, here's R1, here's R2, here's R3, what you're going to notice is and you have in your notes the equation for trying to calculate what the total resistance is. If you notice, if you have a circulation set up in parallel, the resistance actually decreases. So a parallel circuit physiologically increases total cross-sectional area and it decreases resistance. And so why is this going to be important? Or what's the difference in our bodies between series and parallel circulations? Both exist. But by looking at this picture, can you kind of figure out how the majority of our circulation is arranged? In parallel or one after the other in series? If you notice, all the way down, bump, 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 bump. We are set up in parallel. Most of our circulation is arranged in parallel. There are places where it is arranged in series. Obviously, if you go aorta to artery to arterial, that's series. You also, where it's going to be important, I'm going to talk about this next trimester in Physiology 2, is in the kidneys. The way the kidneys are set up, the blood vessels, those blood vessels are arranged in series, and you have a very high resistance there. But that'll be important in the kidneys. You want a high resistance because it's going to result in a very high pressure so you can get filtration. Because the kidneys, that's a big job of those kidneys, is to filter blood. So what we have predominantly, though, is a parallel circulation, which has definite advantages. So you have a little space in your notes to write down what are the advantages of a parallel circulation. So first advantage is for a given pressure gradient, you can get greater amounts of flow through a parallel circuit than through a series. There's something set up in series because you have a lower resistance. So we can get a lot more flow through a parallel circulation than you could through a circulation set up in series. Also, or you just also think about, if I had something that had really, really high resistance and I want to try to get a decent amount of flow, pressures may have to get real high, and we don't want our pressures to be too high all the time because it might damage stuff. The other thing to think about, an advantage of having things set up in parallel versus series, is the circulation with a parallel circulation. You have a wider latitude for altering blood flow through a particular organ without necessarily altering total blood flow through your circulation. So if I needed to increase flow to, say, the quadriceps or anything in your legs, I don't have to necessarily be messing up with blood flow to other parts of my body. If you had something set up in series, what's going to happen is if I say cut down blood flow in one part, it's going to cut down blood flow in everything that succeeds it. And so, like, who's the hierarchy? Who gets the blood first? Who gets it last? It's best that we're all pretty much getting blood at the same time because we're set up in parallel. Now, next to last concept that I'm going to discuss, yeah, you're probably all disgusted by now, but discuss, is types of blood flow. Lamina means sheet. Laminar blood flow is smooth blood flow. If you have turbulent blood flow, that is not smooth. It's just kind of, well, it's turbulent, but try to figure out another way. It's kind of like choppy. It's not nice and smooth. And what you'll know, what happens is with laminar flow, which is mainly what we're going to have in our circulation, is the blood flows in sheets, in layers, one on top of each other. At the surface or right at the vessel wall, the blood will actually flow the slowest because the resistance isn't counted against the wall. It flows a little bit quicker as you move away. So what you notice is kind of drawn a parabola. That's why they call it a parabolic surface. So that's why what you have in your nose is parabolic surface. Is the velocity is higher at the center, and as you move towards the walls, it's slower because of friction. Now, if maybe that blood encounters something like some sort of obstruction on the wall, the flow may become turbulent, and where the layers start to mix. If those layers start to mix, that's going to do, one of the things it does is it dramatically will increase resistance. And what will happen if you increase resistance? What's going to happen to flow rate? That's going to go down. I want you to also think about if I have turbulence in regards to a blood vessel, won't that create a sound? Remember we talked about bruise? If I had, say, a atherosclerotic plaque in your carotid, that will create turbulent flow, which create vibrations, then you can hear. Heart sounds, remember we talked about heart sounds, turbulence creates vibrations. That's what creates the sounds. So we can apply this to things that we've already talked about. The turbulent flow, we do encounter some turbulent flow in our circulation. At bifurcations, you will encounter turbulent flow. Anytime you have a sudden change in vessel radius, you'll get some turbulent flow. If the velocity of flow increases, you have a tendency towards an increase in turbulence. And they're depending on the vessel where it becomes turbulent. It depends, and we're going to be talking about that in a second. So there's like a critical velocity. You will not have turbulent flow until you reach this particular speed before you have turbulence. You also will have turbulent blood flow if you encounter a rough surface along the vessel, like my example was, say, a plaque along the vessel. In regards to this relationship between velocity and the turbulent flow, this is kind of an important concept. And one way to look at it is using something called Reynold's number. So here, do not even attempt to memorize this equation, not in any way, shape, or form. I just want to show you a couple things in regards to Reynold's number. And what Reynold's number does is it predicts the characteristics of the flow. What velocity, this is the big one, at what velocity will that flow become turbulent? That's the biggest thing I want you to get from it. Reynold's number has no units. It's a dimensionless number. It is, or non-dimensional quantity. It describes the type of flow in a fluid. What you'll notice is velocity is on the numerator, and it tells you that as velocity of flow increases, Reynold's number will increase. Well, here's kind of knowing a little bit of numbers. If there is a Reynold's number greater than 200 or 400, again, you notice I don't use any units, you pretty much will only have turbulent flow in places where you change diameter drastically or at bifurcations. If Reynold's number is greater than 2000, you will have turbulent flow in smooth, straight vessels. So it depends on what vessel we are, where we are in your body. But the biggest thing is to realize as you increase velocity of blood flow, your tendency towards creating turbulence goes up. You know, it's a good idea to kind of have a general idea about that 2000 number. If it's greater than 2000, you're going to have turbulence. Even if that vessel is nice, smooth, straight, no plaquing, you're going to get some turbulence. One of the causes of a bruit is high velocity of blood flow. And you may encounter that sometimes with high flow rates, also with people with hyperthyroidism and if you are listening over their thyroid, you may hear a buoy associated with the thyroid because they have large amounts of blood flow in going to that organ. Now, another way to kind of think of this, the relationship between velocity and this tendency towards turbulence, is to think of cars and you're driving. And actually, this Reynolds number applies to the automobile industry, the airplane industry, because they need to know how fast they can take that vehicle before that thing starts to shake off its, shake everything off. So if you've ever been in a car where someone was driving at a very high rate of speed and the car was not designed to be one of those fast cars. I had driven in a, of course they don't make them anymore, they call them a K car, and I think it was like Plymouth or something like that. They were trying to get to like Albany very quickly, and they were driving about 100 miles an hour, and K cars are not designed to go 100 miles an hour. The whole car was shaking. We're like, driving all the way along. Just think of it that way. It depends on how you're designed, and they do this with airplanes too. They have to figure out what that critical velocity is before turbulence goes, because I'm not paying $400 to fly in a plane that the thing is shaking all the time, and I don't want to have to creep along. I want to get there in a few hours. So the same thing applies to other things, not just the circulation. But by looking at this number, I do want to point out one more thing though, besides this velocity, is the viscosity. If you have an increase in viscosity, you'll notice that Reynolds number decreases. But think it this way, if something's very viscous, you're not going to be able to move it that fast, and so your tendency for turbulence goes down. So that makes perfect sense. You're not going to be able to get to that critical velocity. So that one to me kind of makes a little bit more sense. I mean, not that velocity didn't make any sense. Big thing in regards to clinical correlations with turbulent flow and something like work, like the heart. If you have turbulent flow, that requires extra energy. In order to get the same amount of flow rate like you want to, the heart always wants to make sure everybody gets the flow they need. If you create turbulence, that increases resistance, which could decrease flow. So the heart's going to have to work much harder to get the same flow rate. So it has a very good, important clinical correlation to it. Now viscosity, since I already mentioned before about viscosity and its relationship to resistance, I want to talk just one last couple things about viscosity and talk to you about a relationship between vessel diameter and viscosity, which is kind of a weird one. Now, when you think of viscosity, we talked about the stickiness of the blood. And in our blood, our viscosity is caused by our formed elements, predominantly your red blood cells. The water, obviously its viscosity is much less than in our whole blood. Plasma does not have the blood cells in it, so that viscosity is lower than in whole blood. Now, if you apply viscosity to your hematocrit, if you have had your hematocrit done, what hematocrit is the percentage of formed elements in your blood. And say for males, the hematocrit is about 42, girls about 38. So it's depends, males or females. If you notice here, what they do is if you've ever had your blood taken, sometimes they'll take a little bit of sample of your blood, either from your finger or the back of your ear. They'll put it in a little capillary tube and they'll spin it down. What they're doing is they're spinning down those formed elements, and most of those formed elements are red blood cells. And what percentage those blood cells take up of that whole fluid, and here's your plasma, is your hematocrit. So here's, say, a normal hematocrit. If you're anemic, you have a lot less blood cells, your hematocrit is lower. Your viscosity will be lower. If you have the condition called polycythemia, where these people make an abnormal amount of red blood cells, their viscosity is much greater. Their hematocrit's greater, their viscosity is greater. So do you think there's a relationship between hematocrit and flow? Because yes, because hematocrit is related to blood viscosity, which is related to flow. So if I have polycythemia, my blood viscosity is higher. In order to get the same flow, which my heart's going to try to do, it's going to have to work harder to do that. Now, there is a relationship between the diameter of a vessel and viscosity, and it's this thing called the Ferris-Lindquist effect. I will never make you spell that word or those words, so don't be relieved, okay? But Ferris-Lindquist effect. What this is, what the Ferris-Lindquist effect shows us the relationship between vessel diameter and viscosity. So that's one thing I want you to know. What is the relationship between vessel diameter and viscosity? This effect only applies to vessels less than 300 micrometers with the exception of capillaries. So put that in, with the exception of capillaries. I'm going to explain it to you in a moment. Because of the characteristics of tubes or blood vessels and red blood cells, as the blood is moving down to the vessel, because of a thing called axial streaming, the red blood cells will become kind of pushed towards the center, like you see here. They become more concentrated at the center of the vessel during laminar flow. And it has to do with, you know, physics and all that stuff, and I really don't want to get into it, but pretty much it's because of the characteristics, these guys get pushed to the center. So what happens is you have actually a cell-free area on near the sides of the tubes, well, or cell-free zone. And as the lumen of the tube is decreased, that little zone becomes a little bit larger until you get to the capillaries. We're going to mention that again in a second. So what happens is and I'm going to say the apparent viscosity of the blood in those small vessels, like the arterioles, the venules, those things, the viscosity is going to, or apparent viscosity, will be decreased. Because you think, wow, you know, with these small vessels, that we might have a problem with flow. And what they believe is this effect may play a role in decreasing resistance to flow in these smaller vessels. But however, this concept of this Ferris-Lindquist effect does not involve capillaries, which are definitely less than 300 micrometers. The only thing that you have to remember is do a little flashback to cells and tissues. When you saw they had gave you sections of capillaries, and you saw how those red blood cells were moving through those capillaries. They were squeezing through the capillaries. They were bigger than the capillaries, so they kind of fold up a little bit. They're deformable. There is no area on either side for any cell-free area. So those guys are squeezing through the capillaries. So this effect of vessel diameter, as the vessel diameter becomes smaller, the apparent viscosity decreases just because these red blood cells are kind of being pushed away from the wall. So it's decreasing resistance to flow. So it helps things out a little bit. So you might have a little bit better flow than you would assume with vessels this small. Okay, so that's your last major concept. So I kind of want to just briefly state again, because this thing people get confused all the time. What is the Ferris-Lindquist effect? Or what does it tell you? It shows us a relationship between vessel diameter and viscosity. As diameter decreases, apparent viscosity decreases. The Reynolds number shows us the relationship between velocity of flow and the tendency for turbulence. That's what Reynolds number tells you. That's a couple of things that people always kind of get confused about. So those are what those things tell you. It's always important to know what a certain concept tells you, or what's the big picture that you get from that concept? What is it? What kind of illustration do you get? So with Reynolds number, it can predict your characteristic of the flow. Is it going to be laminar? Is it going to be turbulent? So that's kind of things that you need to kind of remember.